All right. Good morning, everybody. I've started the recording, and in a minute or so, we'll get started. Okay. If you're in a position where you're able to, please turn on your camera so that I can see your reactions. That would be helpful. Thanks. How's everybody doing today? Good. Awesome. We're in the back third or so of the semester, so that should be exciting.
We can't see my screen yet.
Oh, we can't see me. That's awesome. There we go. There we go. Yeah, so we're in the back third or so of the semester, which is awesome. You're about what, 5-6 weeks, 5.5 weeks away from graduation or so. That must be exciting, right? For most of you. Is everybody graduating? I don't know if there's any non-graduating senior. Yeah, it's probably rare to take quantum as a non-senior. But cool, that's exciting.
I'm not graduating.
Oh, are you a junior?
I'm taking a 5th year.
Oh, cool. Awesome. All right. Well, most of you are graduating soon. That's awesome. So some quick recap. The last time we met, we talked about how we now have all of the tools that we need to solve the Schrodinger equation and understand sort of what it means. And the last time we looked at something that we call the harmonic oscillator. Essentially just a particle attached to a spring, kind of moving back and forth. And the part that's unique for the harmonic oscillator is the potential, right? This is the harmonic oscillator potential, or sometimes just called the harmonic potential, right? And it looks like kind of like this U shape because the potential is half kx squared, kind of like that. And so when we solve this unique potential, right, it sets up its own Schrodinger equation and it has its own solution. We find a couple of things. One, the frequency of oscillation was 1/2 pi times the square root of that constant k over the mass m. In order to solve this equation, we had to group a bunch of these constants together into what we call alpha, and I'm trying to figure out exactly what alpha is in my notes. Give me a second. We said that we'll let alpha equal to 2m pi to frequency over h bar. So once you did all of that, like anytime you solve the Schrodinger equation, right, you don't just get one function, you get a whole family of functions. And so we label those family of functions with a little n there, and the energy would be related to that, whichever function you're looking at. And those functions look something like this, right? It's alpha over pi. It's one complicated mess, kind of like this. N factorial to the half times a Hermite polynomial, where you use alpha to the half times x for the Hermite polynomial. And then there is an exponential part, e to the minus alpha x squared over 2. The energy is related to this number n again, which is n into the n plus half times Planck's constant times the frequency. So that's a harmonic oscillator. We said that this can mimic molecules vibrating. The only thing that we need to pay attention to, if we have two masses on a spring, so let's say we have mass 1 attached to mass 2, right? In this equation, only one mass appears. So when we want to treat two masses vibrating on a spring, we can imagine one of those masses are fixed, and we can just treat the other one as moving. But in those cases, we can't use the mass of one or the other. We need to use something called the reduced mass, which is the mass of one times the other divided by the mass of one plus the other, right? That's the reduced mass. And that was a harmonic oscillator. We got the potential, we got the frequency, we set up the Schrodinger equation, we got the wave function, we got the energy, and we simplified it to solve for a mass. Now, before we wrap up, there's one more thing I want to talk about. So let's look at the harmonic potential again.
Really, sorry, really quick. Can you show the equation for frequency?
Frequency, all the way up here. 1 over
Okay.
2 pi times the square root of k over m.
Thank you.
All right, let's look at the harmonic oscillator again. Right, let's imagine this is a chemical bond. So this is going to be my first atom that I said would be fixed. And let's say this is my second atom. Right, and they're all connected on a spring. Right, this is a harmonic oscillator potential, which is half kx squared. What does this represent? What does this mean? Well, when you stretch this bond, right, this atom stretches over here and then comes back, and it sort of stretches in this way. What happens if you stretch this bond? Oops, didn't mean to delete that. Stretch this bond farther and farther away, right? No matter how far you stretch it, remember this, it's kx squared, right? So the further you go, it keeps going up and up and up. No matter how far you stretch this bond, there's going to be enough energy there for this ball to roll back down. If you're thinking in terms of a potential landscape, right? The ball is going to roll back down and come back right here, no matter how far you stretch it. In this model, right? So in a harmonic oscillator model, it predicts a lot of cool things. In a harmonic oscillator model, though, you cannot break bonds. You cannot break bonds. Because no matter how far you stretch these two atoms together, it will always roll back. There's, you know, the potential is such that it'll always roll back to where it becomes, where it started from, right? So while it's a good model to understand how molecules vibrate, it's still flawed in that you can't break bonds. And that's a big issue because a lot of chemistry depends on breaking bonds, right? That's a lot of chemistry. Sort of the actual potential that we want to look at is not the harmonic potential, but something called the Morse potential, right? So this is actually the more realistic potential. So let's look at this, the two side by side, right? So let's say this is your potential and this is X, right? This is your harmonic oscillator potential. You're imagining one atom fixed on this y-axis and then the other atom somewhere in this potential. So you can think of X as being the bond length, right? And then you can move this one atom back and forth, changing the bond length as it vibrates. So this would be the harmonic oscillator or HO potential. But like I said, no matter how far you stretch it, it will come back. Let's look at the Morse potential on this side. We're going to set up the same thing. We're going to have potential on the y-axis and the bond length on the x-axis, right? And we're going to have one of our atoms fixed on this and just look at the other one as it vibrates. The Morse potential looks something like this. It flattens out, right? So if you can imagine this second atom stretching, when it stretches over here, what happens? It's on a flat surface. There's no potential to like roll it back down to the valley. In fact, when it's over here, it's allowed to continue and roll away to infinity. So here it lets you break the bond, right? So those are the two differences between the harmonic oscillator potential and the Morse potential. Harmonic oscillator, it does vibrations nicely. Morse potential is a little bit more complex, but it allows you to break bonds because then the particle is allowed to roll away. There is no big mountain for it to roll back down.
So
does that all sort of make, sorry, go ahead.
Does the bond break when you hit the bond length where it flattens out?
This where and when a bond actually breaks is a ridiculously difficult question to answer.
Okay.
If it makes sense in your head, then yes. Let's when it flattens out, that's where the bond breaks. If that helps, go ahead. Actually modeling this and understanding how bonds break is so ridiculously difficult as a theoretical chemist. We don't have good ways to describe this yet. Just in case you wanted, if you were wondering. And the reason why we taught you about the harmonic oscillator potential, even though it doesn't break bonds, is because we have an answer for it. Like mathematicians have found an answer, here's the answer. And it can tell us something about the system. The Morse potential is ridiculously complex, and we don't have like a nice mathematical answer to model this. So it wouldn't make sense for us to look at this in class because we don't have an answer. So let's look at them side by side, right? Morse potential, sorry, harmonic oscillator potential, Morse potential. They're very, very similar. We said that in harmonic oscillator potential, right, you have these energy levels that are equally spaced with n equals 0, n equals 1, n equals 2, n equals 3, and so on, right? Remember, energy is n plus a half times h mu. So the energies are equally spaced and n starts from 0, right? In case you forgot, n starts from 0. In the harmonic oscillator, in the Morse potential, let's write them, sorry, I forgot. Harmonic oscillator potential, Morse potential. In the Morse potential, in the beginning, the energies are very similar to the harmonic oscillator potential. There's n equals 0, n equals 1, n equals 2. They're kind of like similarly spaced. But then once you get closer to here, they start to get closer and closer and closer together. So up here is actually n equals infinity. And at n equals infinity, basically the bond is broken, right? So in this Morse potential, if you give it more and more energy, if you give the vibration more and more energy by increasing the value of n, eventually you're going to break the bond. But if you're looking at the area just on the bottom here, which is where most molecules live in a very low energy state. Then these two models are pretty identical, right? As you can see there, and there's no difference. Or very, very little difference, if you will. So I just wanted to point out those two differences: harmonic oscillator, Morse potential, what they can do, what they can't do. Harmonic oscillator is very good because it gives us a nice answer and a nice energy. Morse potential doesn't, but it allows us to break bonds. Any questions about that one? All right. So far we've looked at the particle in a box, and then we looked at the harmonic oscillator as two model systems to solve the Schrodinger equation. Particle in a box kind of looked at conjugated pi bonds, right? They're very similar to conjugated pi bonds. Harmonic oscillator, this is molecular vibrations, right? The next model we're going to look at and try to solve using Schrodinger equation is called the rigid rotor. And in case you're wondering, rigid rotor would describe molecular rotations. So molecules can rotate, molecules can vibrate, and molecules can absorb their electrons, can jump different energy levels. So the rigid rotor one, we're going to look at that, and then we're going to use that to understand something about how molecules rotate, right? So our objectives for this bit is going to be to find, as you would imagine, all that we're doing for every one of these is find the wave function or wave functions. There are always more than one. Wave functions, energies, that's not how you spend up energy. Energies and angular momenta, because that one's, now we're rotating, so you have an angular momentum of a 2-dimensional and 3-dimensional rigid rotor. in some cases, people will call the two-dimensional rigid rotor a particle on a ring. And people will call the three-dimensional rigid rotor a particle on a sphere. So that's going to be one of our objectives. The second one would be to apply the rigid rotor to diatomic molecules, to rotating diatomic molecules. So let's look at molecules rotating. Let's start with 2 dimensions. And why we don't have a one-dimensional rigid rotor is because how do you rotate in 1 dimension? That doesn't really make sense. So we have to start with 2 dimensions. All right, so let's start with the 2-dimensional rigid rotor, or like I said, particle on a ring. It's always particle somewhere, in a box, on a ring, on a sphere. I guess we could call a harmonic oscillator particle on a spring. I'm going to coin that one. Particle on a spring it is. All right, so we're rotating in 2 dimensions. So imagine you have a particle, I don't know, tied to a string or something, to a fixed point, and it's rotating around that point, right? We're going to call this the y-axis, because why not? We're going to call this the x-axis. So there's our particle on a ring. This particle will have mass m. All particles will have mass m, right? Just to symbolize it. There is no potential. We're going to just assume that it's rotating on a ring, and we're going to assume that the radius of this ring r is fixed. That's all we're going to assume. What's always the first step in any of these problems? Write the Schrodinger equation. So the Schrodinger equation, it's the Hamiltonian times the wave function is equal to energy times the wave function. We need to figure out what the Hamiltonian is, right? The Hamiltonian is the kinetic energy plus the potential energy. Now I said that the potential energy in this case is going to be 0. We're not going to worry about that. So we just need to worry about the kinetic energy. But so we know that the kinetic energy is negative h bar squared over 2m times nabla squared, right? This is moving in 2 dimensions, x and y. So this nabla squared, if we want to write it out explicitly, would be d squared dx squared plus d squared dy squared. So that's our h bar. So if we write out the entire Schrodinger equation, it's going to be negative h bar squared over 2m d squared dx squared plus d squared dy squared times the wave function is equal to the energy times the wave function. And now we need to find what wave function satisfies this equation. What wave function, when you take the second derivative of x and you add it to the second derivative of y, you get back the same wave function. And you're probably wondering, is there such a function and all of that? But here's the thing. This is of x and y, it's too complicated. I'm sure somebody could solve it. Not me and not in this class. It's too complicated because we have 2 variables to consider. Variables, x and y. That's too much. I can only think in one, x or y, not both. So how do we simplify this? Well, the way to simplify this is actually to use polar coordinates. And I assume that everybody's at least heard of polar coordinates, maybe used it a little bit somewhere. But let's use polar coordinates. Right? In polar coordinates, it's the same setup. Here's our ring, here's our particle, going around the ring, right? But instead of x and y in polar coordinates, what we have is the radius and the angle. We're going to call that phi. So in case you're wondering, instead of the wave function now being in terms of x and y, we've moved to a wave function in terms of the radius and the angle because we're moving in polar coordinates. But r is fixed. It's a constant, right? So we don't even have to worry about r being a variable. So that means that we actually simplify this further, and it's kind of like a one-dimensional problem where the wave function only needs to worry about the angle, right? Because r is never going to change. We said it's on this string. So this will simplify our problem a lot. In this setup, x would be r times cosine of this angle, and y is equal to r times sine of this angle, in case you forgot how to like convert between polar coordinates and Cartesian coordinates, x, y, z, right? There are a lot of other neat little tricks that we're not going to derive. I'm just going to tell you what they are, and you'll have to trust me. So this differential here, right, plus d squared dy squared. In polar coordinates, this becomes d squared dr squared plus 1 over r d squared ddr, not d squared dr, but ddr plus 1 over r squared d squared d phi squared. So this in Cartesian coordinates becomes this in polar coordinates. So this is Cartesian coordinates, and this is two-dimensional polar coordinates. Everybody with me so far? So remember our Schrodinger equation all the way up here has this d squared dx squared d squared dy squared. So I'm going to just replace that with the polar coordinate equivalent. So it's negative h bar squared over 2m. That part doesn't change. But instead of this, we have this stuff over here. D squared dr squared plus 1 over r ddr plus 1 over r squared d squared d phi squared. All of that times the wave function should be the energy times the wave function. And you're probably thinking, we just made this more complex, didn't we? But here's the thing. We said that r is fixed. R is fixed. R can never change. Remember what dr or dx or dy or any of that means? It means a small change in x or a small change in y or a small change in r. But if r is fixed, there's no such thing as a small change in r. Dr doesn't exist. So if that's the case, that doesn't exist, that doesn't exist, and all that we're left with is this equation times 1 over r d squared d phi squared. That's the Hamiltonian, that's the wave function, that's the energy, and the wave function again. We've simplified, sorry, this should be r squared. We've simplified it by a ton. And now that you know, now in here, we're only working with a derivative with respect to phi, this angle. Now, when things are rotating, we want to use the moment of inertia. Oops, inertia. Usually given by the symbol I. And I is the mass times the radius squared, kind of like that. So here's the mass, here's the radius squared. So I'm just going to rewrite this as negative h bar squared over 2 times I, right? I is the moment of inertia times the second derivative times the wave function, which is going to be the energy times the wave function. Just to simplify it, we're not going to worry about the mass anymore. We're going to worry about the moment of inertia. So here's where we are. And that's the Schrodinger equation. And now that is probably one that we can solve. So now we need to think what function, when you take the second derivative with respect to some variable, in this case it's phi, you get back a constant times that same function. What function satisfies this? We did cosine and sine and all of that works. The general case here is the wave function is going to be some constant, we call it a, times e to the I m phi or phi. E to the I m phi. I don't know Greek. I think some people call it phi. So here, a and m are constants. So this is the reason I use m not n is going to become clearer later on, but this m is not the mass. So not mass. Remember, mass is already wrapped up in this I over here. This m is not the mass. It's going to be a quantum number once we solve it, and there's a reason why we use m. But that's going to be our answer. A is equal to I m phi. All right. So are we done though? Well, not really, because what is A and what is M? We don't know. Let's look at this particle in a ring again, right? Let's say the particle starts here at 0 degrees, right? And it rotates around counterclockwise. Whatever it's doing here, it will do stuff as it goes around. But when it comes back here to 0 degrees again, it must be doing the same thing as before, right? It has to be cyclical. So that relates to 2 pi, that's 2 pi degrees, right? It goes around the whole circle, that's 2 pi. So whatever the wave function is doing, when you add 2 pi to it, it should be the same as when you don't add 2 pi to it. Like when you make a full circle, it has to go back to where it was before. So we need to set up this situation. Any angle plus 2 pi should be the same as that angle. The whole thing is cyclical, right? So let's plug in our wave function. We call this a cyclical boundary condition. Just like in a particle in a box, we use boundary conditions where the edges must go to 0. Here we have a cyclical boundary condition where once it completes a full circle, it must go back to what it was. Everybody with me so far?
Really quickly,
All
could
right.
you explain?
Could I explain?
So we don't know I or M, or is I?
I is a complex number.
Oh, I gotcha. Sorry.
I is a
So
complex
we don't know.
number. We don't know A or M.
We don't know A or M. Okay.
Right. And those are right now what we're going to do is try to find what A and M are.
Gotcha.
A and M are. That sounds weird. All right. So we're going to try to figure out A and M, and that way we'll know the whole wave function. All right. So psi of this thing here would be A times e to the I times m times phi, but now phi is this phi plus 2 pi, right? And on this side, it's a, let me delete that part, a times e to the I m phi. So this is the wave function at just phi, and this is the wave function at phi plus 2 pi, right? All I did was change phi into phi plus 2 pi. And we, because of the cyclical boundary conditions, those two things should be identical. In the way that we've set up this equation, a can cancel out and we can focus on e to the I m phi plus 2 pi is equal to e to the I m phi. When you have an exponent that's added up like this, you can separate it into two sort of products of exponents. So this will be e to the I m phi times e to the I m 2 pi, right? And on this side, it's e to the I m phi, kind of like that. And again, you can see that this will cancel out with this. So we have e to the I m 2 pi is equal to 1. Okay. Now, I don't know if you remember exponential identities and trig identities and all that, but e to the ix, if you remembered, would have been cosine x plus I sine x, I think. Let me just verify that's correct in my notes. Yes, that's correct, right? So if we let basically x be equal to all of the stuff that's not the I, right? Then we find that e to the I m 2 pi is the same as cosine of 2 pi m. I'm just rearranging it, plus I times sine of 2 pi m. And according to this equation up here, that should all be equal to 1. So we need to figure out when is this equation, which values of m makes this equation come out to 1. So that means this happens when cosine of 2 pi m is equal to 1, because this is real. This is real. This is complex. So that means that sine of 2 pi m would be equal to 0. So when is cosine of 2 pi m equals 1 and sine of 2 pi m equals 0? Well, these things happen at, let's say all of that is called theta. It happens when theta is 0 or 2 pi or 4 pi and so on. So that gives us a, I'll write it in a better way. So cosine of 2 pi m equals 1 happens for 2 pi m equals either 0 or plus or minus 2 pi or plus or minus 4 pi. I'll do one more, plus or minus 6 pi and so on. This means that m, if you divide everything over here by 2 pi, m should be 0 or plus or minus 1 or plus or minus 2 or plus or minus 3 and so on. Right?
Could you
You
zoom
could do
out
the same
some?
with the sine part and it will come out to be exactly the same.
Could you zoom out
Sorry.
some?
Oh. There we
Thank
go.
you.
So is m like n, but it can be negative as well?
Yes. So m is kind of like, and again, this is all of these are what we call quantum numbers. They come out to be something in all of these cases so far, whole numbers. But m can be negative. All right. And then so we're at this point now in our wave function, right, is a times e to the I m phi. And we learned that m is either 0 or plus or minus 1 or plus or minus 2 or plus or minus 3. And you get the idea. We still don't know what a is though. A we get from normalization, right? Remember the wave function must be normalized. So the integral of the wave function star, the wave function, it's not x now, it's phi, d phi, right? And the limits of the integration doesn't go from like 0 to infinity or whatever. It's an angle. It goes from 0 to 2 pi. So this integral should be 1. Everybody still with me? All right, so let's find this integral going from 0 to 2 pi. It's this complex conjugate times itself, the wave function. So it's a times, remember the complex conjugate, whenever you see I, you change it to negative I, so it'd be negative I m phi times the original wave function, e to the I m phi, d phi, right? But this is e to the negative something times e to the positive of that same thing, that goes to 1, right? Like e to the negative x times e to the x is 1. Because remember, that's e to the x minus x, which is equal to e to the 0, which is equal to 1. So this whole part, that all becomes 1. So really, this simplifies to 0 to 2 pi. The integral of a squared d phi is equal to and we need to find that. Well, it should be equal to 1, right? So what's the integral of a squared d phi? It's a squared times phi. Kind of like the integral of 1 dx is just x, right? It's a constant. But this integral must go from phi equals 0 to phi equals 2 pi, and that should all be equal to 1. So that becomes a squared into 2 pi minus 0 is equal to 1. So that means that a squared times 2 pi is equal to 1. It means that a squared is equal to 1 over 2 pi, or a is equal to 1 over square root of 2 pi. Will you need to remember how to derive this on an exam? No. Should you know how to derive it? That's debatable. But I want to show you, I don't pull these numbers out of thin air. These wave functions, the reason why we're studying them is because they're all not so difficult to solve. And the wave functions that we end up pulling out for these are not crazy. So if we write the whole wave function now for this particle on a ring, it has this quantum number m, right? It's a function of the angle phi. A is 1 over square root of 2 pi. So we know that. And it's e to the I m phi, where m, sorry, not phi, m is either 0 or plus or minus 1 or plus or minus 2 and so on. So that's our wave function. So that's the wave function of a particle on a ring. What did we say we needed to do? We need to find a wave function. We also need to find the energy. So what about the energy? Well, let's do that right now. We know that the Hamiltonian times the wave function will give us the energy times the wave function. I'm putting little m's there because we know that there's not just one, there's a whole class of them with respect to the quantum number m. Can I move this up? Yeah. Cool. The Hamiltonian we said was negative h bar squared over 2i times the d squared d phi squared times the wave function. So let's figure out this, and that will give us the energy, right? So it will be negative h bar squared over 2 times the I, which is the moment of inertia, the second derivative with respect to the angle, times 1 over square root of 2 pi e to the I m phi. All right. So this here is a constant, doesn't change. This here is a constant, so I'm going to pull it out, 1 over square root of 2 pi. So we're looking at the second derivative of that stuff. So if we're going to do the first derivative of this with respect to phi, right? So d phi of e to the I m phi, it comes out to be just I m times e to the I m phi, right? And if you take another derivative, so the second derivative, it just becomes I m squared times the same function, right? That's why we went with exponentials. Their derivatives and integrals are easy to work with. So that whole second derivative, if I put it over there, it becomes I m squared e to the I m phi. So I'm going to rewrite this again. Negative h bar squared over 2m, not m. I'm so accustomed to writing 2m. 2i, moment of inertia, times this 1 over square root of 2 pi. I m squared. M is a quantum number, right? Not the mass. Remember that. This is why your textbook uses m. I would have used n or something else. But I squared is negative 1, right? That's the complex number. So I squared is negative 1, and then there's m squared. So it's negative m squared. That's what that comes out to be. And then e to the I m phi. All right, I'm going to simplify this. The negative sign here, the negative sign there goes away. So we have h bar squared m squared over 2i, and then all of this stuff. square root of 2 pi, 1 over square root of 2 pi, e to the I m phi. But remember, this part here, that's just a wave function. So we have h bar squared m squared over 2i times the wave function. So this means that our energy is h bar squared m squared over 2i. So this is the energy for a particle on a ring. So a lot of derivations, but I want to show you that once you have the tools that we have been using, like once you understand, all we got to do is find a Hamiltonian, set up the Schrodinger equation. The rest is calculus and algebra, which mankind has known for hundreds of years. So hopefully we can solve it from that point. But the unique part is being able to like set up the Schrodinger equation and the Hamiltonian. So we have the wave function, we have the energy now. What else did we said? There was one other. Well, before I do, there was one other thing we're gonna find. But before I do, I want to make a point of something. We know that m could be positive and negative. M could be positive or negative, but the energy is only positive because there's m squared. So if m is negative, it becomes positive anyway, right? So we don't have a negative energy. So that's one thing I want to point out. The second thing that I want to point out about this, every level of m except for m equals 0. So m equals 0 leads to an energy of 0. That's the 0 point energy for a particle on a ring. It has 0 energy. But for m greater than not m greater than 0, but for the absolute value of m greater than 0, so plus or minus 1, plus or minus 2, plus or minus 3, all the levels are doubly degenerate. Remember what degenerate means? The energy levels are identical. So if you have an energy of +1 or m of +1 or m of -1, the energy is the same. An m of +10 or -10, those energies are the same, and so on and so forth. Right? If you were to try to model what's happening there, right? Let's say this is a particle moving on a ring. M equals plus, let's say +1, or any positive number correspond to a particle moving counterclockwise, whereas m equals to negative numbers, I'll put greater than 0 and less than 0, means the particle is moving clockwise. But basically, they'll have the same energy if the m values, the absolute values of m are the same. Things could rotate clockwise or counterclockwise with the same rotational energy, right? So that's why we have both positive and negative, in case you were wondering. It corresponds to particles moving clockwise or anti-counterclockwise on this little ring. In terms of what these wave functions actually look like, those are very near impossible for me to draw. Your textbook has a couple of examples, and the next Jupyter notebook lets you generate any of these wave functions with positive or negative values of m, and it's actually moving and rotating, so you can actually see how they move and rotate in three-dimensional space, right? So when you play around with the next Jupyter notebook, you'll actually see what these wave functions look like and how they move and rotate around in a circle.
Good question. So
Yes.
the way you have the, no, never mind. Never mind. I'm good. Figure it out.
Go ahead.
Nope,
I said
figure it out. We're
clockwise
good.
and counter. Okay, I said counterclockwise and clockwise, but that depends on which side you're viewing this whole thing from, right? If you view it from the other angle, the rotation will seem to be the opposite way around, if that's what you were getting at. You have to choose some convention, honestly. So this is the convention that I chose because it lines up with the x and y equations that I set up earlier.
Okay.
For positive and negative phi. But yeah, it depends on what angle you're looking at the rotation. All right. So with that, we're gonna I want to pause there because we did a lot of derivation, but I want to have you like practice some questions. I want you to find what are the energies of the two lowest energy states. Sometimes people call these eigenstates. Basically, they add eigen in front of anything when it's an eigenvalue problem. Energy states of an electron on a ring. So basically the problem we just solved. And the ring has a radius of 1.0 angstroms. So the energies of the two lowest energy states or eigenstates of an electron on a ring with radius 1 angstrom. Remember, the energy equation for this is h bar squared m squared over 2 times the moment of inertia. M can be 0 or plus or minus 1 and so on. So I want the energy in joules, right? So let's see if try to work that one out, see if you can figure it out. And then I'll go over it.
Do you want us to do the 0 point? Like, is the 0 point included in the two
Yes,
lowest?
the 0 point, sorry, the 0 point is the lowest energy. So yes, the 0 point would be one of the answers. And for m equals 0, the particle is not rotating either left or right. It's just standing still. It's quite boring, actually. Which is a valid solution, right? Like a particle can just stand still. It can do whatever it wants. While you guys are working on that, over this past weekend, I've thought of an idea for a computer game that I'm going to try to program this summer, where it's going to be like a platformer, but instead of like, I don't know, like Mario, where you just jump around on stuff, you're going to be like a wave. It's an idea. I'm going to try to code it. And then I'm going to give up halfway through because that's usually how my coding projects go. So I forgot who asked the question, but yes, one of those energies are going to be the 0 point energy, which is just zero energy, like I mentioned earlier, right? So for the m equals 0, this whole thing just becomes 0 joules. I have to be careful because 0, right? I put a little dot in it so you don't think it's an O or a line, but then phi looks like that. So I have to be careful that I don't mix those two up. So let me know either by, I don't know, doing something, maybe in chat or something. Let me know when you're done.
Quick question. What's the conversion for angstrom to meter? Is it 10 to the minus 10?
Yes. 1 angstrom is 10 to the minus 10 meters. So we're going to be solving 4 different systems using the Schrodinger equation. We've already done 2, and this is the third, right? Particle in the box, harmonic oscillator, rigid rotor is the third. And then finally, after we've done those 3, we have all the tools we need to solve the simplest atom in existence, which is the hydrogen atom. And then after we solve the hydrogen atom, we're going to start looking at more complex things like the helium atom, which is way too complex. And we're going to look at other things. And I don't know, since we have about a third or so semester left. Once we solve the helium atom, or we won't solve the helium atom, but we're going to look at approximate ways that people solve things like the helium atom, and then that will give you, we'll start looking at some approximations for how we do spectroscopies, right? Like IR spectroscopy, UV vis spectroscopy, Raman spectroscopy. We're going to hit on some of those. If you have a type of spectroscopy, because I don't know if we have enough time in the semester to go through all of them. If you have a specific type of spectroscopy that you've used over your 4 years here at UIndy, and you want us to go into the principles of that one specifically, just send me a message and I'll make sure we hit it. Otherwise, I'll just go over them in the order that they're in your textbook. So if you think, oh, I don't know, IR spectroscopy and it was really cool, send me a message and be like, hey, can we make sure we hit IR spectroscopy? Stuff like that. Sounds good? All right. Because yeah, like I said, I don't think we have enough time to do all the types of spectroscopy. So the next level up was E1. And this will be h squared, 1 squared, right? Because m is 1 over 2 times the moment of inertia. We know what h is, h bar, sorry. We know what that is. So we just need to figure out the moment of inertia, which is the mass times r squared. It's an electron, right? So the mass is the mass of an electron, which is 9.109 by 10 to the minus 31 kilograms, I think. Yes. R is 1.0 by 10 to the minus 10 angstrom, meters, sorry. I converted to meters squared. So this all comes out to be 9.109 to 2 sig figs by 10 to the minus 40, I think it's 49 kilogram times meter squared, right? Because meter squared. Let me know if I made any mistakes. When I do these practice problems, I punch numbers in very quickly. So the energy state then is h bar squared, which h bar we know is 1.05 by 10 to the minus, no, is it? I have to look this up, I forgot. H bar 1.05 by 10 to the minus 34. Okay, there we go. There we go. My 10 to the minus 34 joules times seconds squared over 2 times 9.1 by 10 to the minus 49 kilogram meter squared. I'm going to put the square in there, and then I'm just going to be, this is joule squared, second squared, right?
Sorry, why, or maybe I'm not doing the conversion right in my head, but would it be to the negative 51? Because you square the negative 10 and then that's negative 20 and then negative 20 plus negative 31.
Yeah. Oh, yeah, no, you're right.
Okay.
In my notes here, I somehow have angstroms is 10 to the minus 9. You're right. 10 to the minus 10. So this would be 51. So hang on. I was thinking of nanometers. Good catch, thanks. So this would be 51. So somebody help me to figure out what all this comes out to be now, because my calculator is not nearby.
I got 6.105 times 10 to the negative 19th joules.
All
I
right,
got the same.
cool, thank you. Yeah, I had 10 to the minus 9 in my notes here for some reason. That makes more sense, actually, 10 to the minus 19. So how do we end up with joules, by the way? Kilogram, meter squared, second squared, that's all joules, like, or 1 over joule. So that will cancel out with one of the joules up there. And so we end up with joules. And this is for m equals 1 we used, but the answer will be identical if it was m equals minus 1, right? So negative 1 is also the same as that. Positive 1, negative 1, they have the same energy. Does it all make sense? Thanks for those. In my notes, I don't know why I have 1 angstrom is 10 to the minus 9 meters for some reason. Okay, so that's the energy. The formula is pretty straightforward, and in any exam or test, you will get the formula. You just need to know how to use it. But there's one more thing that we want to talk about. I mentioned earlier, one of the objectives is to learn about also the angular momentum. This is something new because none of the particles that we looked at before were rotating. You can only have an angular momentum if you're rotating. So what about the angular momentum? Earlier, I think in one of the chapters, I mentioned that the angular momentum, the operator for the angular momentum looks like this. It's x, the operator for x times d dy minus the operator for y times d dx. That's the angular momentum. But we can't use this because we need it in polar coordinates. So in polar coordinates, the same angular momentum comes out to be negative IH dd phi. So much easier. So let's find the angular momentum. If we want to find the angular momentum, we just take the angular momentum operator and operate it on our wave function. And we'll put a little m there because the wave function depends on m. So that will be negative I h bar dd phi of 1 over square root of 2 pi, right? I'm now writing out the entire wave function, e to the I m phi, like that. So let's do this. Let's resolve this. So it's negative I h bar. The 1 over square root of 2 pi doesn't change, it's a constant. The dd phi of this guy comes out to be Im e to the I m phi. We did that earlier. So this whole thing comes out to be negative IH bar times Im. The I here and the I here multiply to give us negative 1. And that negative 1 with this negative 1 gives us a positive 1. So this whole thing comes out to be H bar M, right? This and this comes out to be H bar M. And then you have 1 over square root of 2 pi times e to the I m phi. So basically, this here is the wave function, and this is h bar m. So the angular momentum is h bar m. Remember, m could be 0, or plus or minus 1, or plus or minus 2, and so forth.
But since m isn't squared here, the plus or minus does matter in this case, but that just translates to which direction it's going.
Yes, exactly. So in angular momentum, you can have momentum in a negative angular direction or the positive angular direction. For those of you wondering why positive means going counterclockwise and negative means clockwise, this is how we count angles, right? Angle starts at 0 here, and we count, like, measure angles going that way. So like that would be 45. That would be 90 degrees. The angle keeps going higher and higher as we go counterclockwise. So that's why a positive value of n just means that we're going counterclockwise. It's not that, like, that's a convention that we use in math for some reason. Like, this is not 0 degrees, and then this is not 45 degrees. Somehow this is negative 45, in case you're wondering. It's interesting how we choose some conventions for things just randomly. But there's the angular momentum.
Could you zoom out?
Yep.
Thank you.
So a couple things somebody already pointed out. Angular momentum can be negative. And basically also angular momentum only depends on m, the quantum number. The energy had the little I in there. Where are we? Up here, energy had I, which is, the mass and the radius and all of that, right? But the angular momentum doesn't care what the mass is, doesn't care what the radius is. It's just depends on the quantum number m. So to summarize, two-dimensional particle in a box. Summary of, we'll call it two-dimensional particle in a box. No, two-dimensional rigid rotor or particle on a ring, right? We're using polar coordinates. We have a wave function that is this. M is 0 or plus or minus 1. I keep writing these same things over and over again, just in the hopes that it sticks. The energy is h bar squared m squared over 2I. And the angular momentum is just h bar m. And hopefully we all remember how we got to this point. You can also put this as a function of the angle only, in case if you wanted to. So if you see those three equations somewhere on the equation sheet, you should be able to quickly recognize what they belong to. All right, so two-dimensional particle on a ring. Now we move on to three-dimensional particle, rotating particle, which we call particle on a sphere. Any questions on particle on a ring before we move on? No? Okay. So let's do that. So it's 3D rigid rotor or particle on a sphere. Every time you add a dimension, the problem gets a lot more complicated. One dimension, easy. Two dimension, complex, manageable. 3D, things are crazy. It would be so much easier if the world was only one dimension. All right, so we have three-dimensional. This is going to be hard to draw because it's not just a circle, but imagine you have a sphere. All right, this is my sphere, if you can imagine that as a sphere. And you have your particle stuck on the surface of this sphere, right? So, I don't know, maybe like that. You have a particle, like a surface of a ball or something, and the particle is stuck to the surface of the ball, right? So the radius here, whatever that radius is going to be fixed again. Radius is fixed. Right? Now we're not going to work in XYZ or Cartesian coordinates again, because that's going to just be hell to solve. But in this situation, there are going to be two angles, right? There's going to be the phi angle that we looked at before that tells us how much the particle goes around in this X and Y direction. If you imagine that, this is X, this is Y, and then if you go in and out of the page like that, it's Z. Right? So the phi angle tells us how much in the X and Y direction we are. And then there's another angle here, we'll call it theta, that sort of tells us how much in the Z direction we go. In these polar coordinates, phi as we learned before, goes from between 0 and 2 pi. But to make the complete circle, theta only has to go between 0 and pi. Like that. And this is all spherical polar coordinates. Right? We looked at two-dimensional polar coordinates. Again, these are all if you did these sorts of math, they might be very familiar to you, but we're not here to do math. We're just here to use it use it to solve problems that we're interested in. In this sort of coordinate system, x is r times sine theta times cosine phi. Y is r sine theta cosine, not cosine, sorry, sine phi. And z or z is r cosine theta. So that's how we translate between Cartesian and polar coordinates. Of course, we're not going to do all the algebra to translate everything for you, but in short, the Hamiltonian would be negative h bar squared over 2i nabla squared, right? Which is equivalent to negative h bar squared over 2i. And in Cartesian coordinate, it'll be d squared dx squared plus d squared dy squared plus d squared dz squared, because we need to look at motion in all three directions.
Sorry, just to clarify, so V is the angle between x and y, and theta is the angle between x and z?
Or y and z, right? There depends on how you rotate it. It's the same thing, but yes. X and z or y and z. Basically, it's the angle between the plane of xy and the z-axis. So there we have it, polar coordinates. That's a Schrodinger equation. If we wanted to transform these Cartesian coordinates into polar coordinates, we know that this d tau that we usually use for stuff is the same as saying dx, dy, dz in 3 dimensions, right? In polar coordinates, that whole thing comes out to be, and you should try to remember this one, r squared sine theta dr d phi d theta So yeah, something as simple as dx, dy, dz comes out to be that complicated thing, dr, d phi, d theta. So you can integrate for r, theta, and phi. And then something like nabla squared, which we know is d squared x, dx squared plus d squared dy squared plus d squared dz squared. In polar coordinates, that comes out to be 1 over r squared d squared d theta squared plus cotangent of theta d d theta plus 1 over sine squared theta times d squared d phi squared. So these problems always look a little bit horrible and worse than we started with when we're trying to solve them. But this is the Hamiltonian up here, but we wanted to go to polar coordinates. So this is what this nabla squared would look like in polar coordinates, 3 dimensions. So if I were to rewrite that Hamiltonian, right, it's negative h bar squared over 2i, that part doesn't change. But in here, we have this stuff in the square parentheses. Remember the r squared, sorry, this should be m up here. The r squared joins with the m. The I just comes when we switch to polar coordinates. The r squared joins with the m to give us the I outside here. So this r squared with this m gives us this I. And then everything else in the parentheses remain the same. D squared d theta squared plus cotangent of theta times d d theta plus 1 over sine squared theta d squared d phi squared. So that's where we live right now. My question to you now becomes, what function, when we use this Hamiltonian on it, we get a constant times the wave function. What function solves the Schrodinger equation? What function solves that equation? What is phi? Psi? No, we're not gonna go derive this because honestly, I don't even know if I know how to do it. It is quite complex. So I'm just gonna tell you the answer. The same way I did it for when we did the harmonic oscillator, I just told you what the answer was. So there's a couple of things. Before I tell you what the answer is, there's a couple of ways we can think about this. The wave function will have r, phi, and theta, right? Instead of x, y, z, it's r, phi, and theta because it's spherical coordinates. But we said that r is fixed, so basically the wave function should just be in terms of phi and theta, right? So r is fixed. R doesn't change. The radius of the sphere doesn't change. All right. Remember when we solved the 3D particle in a box, we said that this wave function of x, y, and z, we can rewrite it as some function of x only times some function of y only times some function of z only. We separate the variables. So this is called separation of variables. We're going to do the same thing here, right? We're going to assume that this wave function of phi and theta can be written as some wave function of only phi, and this is capital Phi, that's how you write capital Phi, times some wave function, that's capital theta, of just theta. We're going to separate the variables like that. When you separate variables, things start to look easy, right? Or easier. Now, if we separate out the phi part, it's kind of like we have a particle on a ring, right? We're ignoring the z direction. So this phi part is exactly the particle on a ring, the particle on a ring answer. E to the I m phi. Remember, m here goes from 0, positive, -1, and so on. So this is little m right there. So the phi part, we already know what the answer is. It's the particle on a ring answer. What is theta? To make this all work, we need to find theta. Again, I'm not going to derive theta because we're going to be here forever. Probably. I don't know. I've never actually tried deriving it for myself, honestly. But theta, mathematicians have derived it for us. They've done all this sorts of problem before, and that's why we love them. They've done the hard work, and they figured out theta, the theta that makes all of this work, are called the associated Legendre polynomials, right? And usually they have two numbers associated with them, L, and we're going to call the other one ML, like that. So it has two quantum numbers. And I'm gonna, hang on, before I do that, let me do this. So the L number can take on values of 0 or positive integers, and the ML number can take on values from -L through 0, whole numbers, through the positive L. Or in another way of saying is, the absolute value of ML should be less than or equal to L. This is starting to look like quantum numbers that you guys did in Gen Chem, by the way. And remember I said we need to solve all these different kinds of problems before we go on to the hydrogen atom. There's a reason why all of this starts to look at like what we do for hydrogen atom. So there are two types of quantum numbers here, L and ML that depends on L. And the reason why we use M up here is for this to work, this M also needs to be identical to the ML value from below. So ML here should stop at L from below. So it's kind of like the particle on a ring, but it's limited, right? So those are the two parts. The wave function has a phi part and a theta part. The phi part kind of like particle on a ring, except the ML is limited. The theta part has L and ML on it. So the wave function depends on L and ML for theta and phi, and it becomes 1 over the square root of 2 pi times e to the I ml phi times these associated Legendre polynomials. So what are the associated Legendre polynomials? I'm just going to write some of them. Here we're going to have values of L. Here we're going to have values of ML. And here we're going to have values of the polynomial L, ML in terms of theta. So for L equals 0, ML could only have one possible value, right? 0. And the wave function just becomes 1 over 2 times the square root of 2, or square root of 2 of 2, however you want to look at it. We'll look at L equals 1. In that case, ML could be 0, in which case the wave function is 1 over 2 times the square root of 6 times cosine theta. In the case where L equals 1, but ML is either plus or minus 1, the that function is 1 over 2 times the square root of 3 times sine theta. We're going to do up to 2. For L equals 2, ML could be 0, in which case the theta wave function becomes really complicated really quickly. Square root of 10, and I hope I didn't I copied all of this correctly down, but that's what it is. For L equals 2, ML equals plus or minus 1, the wave function is 1 over 2 times the square root of 15 times sine theta times cosine theta. And finally, L equals 2, ML equals plus or minus 2, the wave function is 1 over 4 square root of 15 times sine squared theta, like that. Note that in all of the cases for the theta part, the plus and minus of ML doesn't matter. It only matters for the all the way up here. It only matters for this part. If the ML is plus or minus 1, this will have a plus or minus sign up here. But those are the associate Legendre polynomials. They're also in your textbook, and you can Google them online. They've already solved them so that the whole equation, the whole wave function is normalized, so you don't need to worry about that. But we'll stop there. If you want to practice, try punching in various numbers of L and ML to try to write the wave function for that particular set of quantum numbers. Remember, there's this part, and then there's the associate Legendre polynomials. Some some people have sort of simplified all of this into one set of function. They call it, we'll give it a symbol y. There's still two wave functions, L or ML, two variables, theta and phi. And they call these spherical harmonics. So you multiply this part by this part, and you have a new set of function called spherical harmonics. So in case you see this somewhere, they refer to the same thing. It's actually a quicker way to write it all. So there we have it, the wave function for a three-dimensional particle in a box. No, three-dimensional particle in a sphere. There we go, particle in a sphere. The next time we come back, we'll look at the energy for this particle in a sphere, and we'll look at the angular momentum for this particle in the sphere. Sounds good? I know we did a lot of derivation, and we went into polar coordinates today, which sometimes make my brain hurt. So hopefully you get some chance to digest that. Until next time, I'll see you Thursday.
Dr.